So we're back to Visual Studio, and what I've done is I've created another project called Hello CUDA, and this time I actually removed all the boilerplate code that the default template added for us. So all I have here is two include statements up above, which are pretty much essential to any kind of CUDA manipulation that we actually want to do. Now we could go and take a look at what those include statements are, but before we do, I want to point out this external dependencies folder. So essentially, the external dependencies folder contains references for a large number of headers, both headers which are part of the standard library and the standard libraries that Visual Studio comes with. So you would have something like math.h, which, as you can see here, references the include folder in Visual Studio, but also we have a few headers which are CUDA specific. So for example, atomic functions for shader model 1.1 and stuff like that. And two of those headers are actually included here. I'd like to point out that you cannot press Shift Control G and open the header as you would if it was a normal Visual Studio project. It simply doesn't work here. And in fact, throughout this recording, you will see a few problems that Visual Studio has when parsing and analyzing the CUDA related code. But you can always deduce that this CUDA runtime.h is actually found somewhere here. So we can open CUDA runtime.h, and we can see that this is another header containing even more headers, so we can open built-in types. And by the way, here we can use the open document reference shortcut for some reason. So we can see that this has even more types. Let's go into device types, and then we can see that this class has just one definition of an enum, which, well, let's try something else. Let's try vector types. So this has lots of aggregations of different types that we might want to use with alignment specifications and so on. And there's only one type here that we are particularly interested in, and that is dim3, this type, because this is the type that's used to specify dimensions for both the grid as well as the block size for a kernel launch. So let's close all these types for now, and I want to show how to actually write CUDA C programs to do something in parallel on the GPU. But we're going to start with something on the CPU, because that's kind of it's simpler to understand the transition from kind of simulated parallel code, shall we say, to real parallel code. So I'm going to create a little application that adds two arrays, just like the CUDA boilerplate sample. But we're going to do it on the CPU to begin with. So we're going to have a few elements. Let's have 5 elements, for example. And I want to basically add two arrays into a third array. So I would have an array A with values, let's say 1, 2, 3, 4, and 5. And I would have an array B with values, let's say 10, 20, 30, 40, and 50. And we will have an array C, which is going to contain the result of the addition. So we're doing this on the CPU for now, so we can create a function. Let's call it add arrays CPU. Let's just call it add arrays, and we're going to provide this function with the A and B arrays, the C array where to store the actual data, as well as the number of elements that we want to add up. So let's go up here and actually define this function. Remember, we're doing this on the CPU, no GPU code of any kind here. So we're adding two arrays, so an array A and an array B, and we're putting it into an array C, and we have count elements. So here, if you're doing this on the CPU, you would have a simple for loop, something like for I going from 0 to count plus I. We say that C at I equals A at I plus B at I, like so. And let's actually output these values. Now we can use one of the headers that is in the external references. So I would include, let's say, standard.io.h here, and let's actually write these out. So I'm going to let me copy the for loop here. So for each of the elements, we're going to printf %d space C at I, and then we'll pause the output. So let's run this. Alright, so as you can see, the addition has been done successfully and it's been done on the CPU. Now, if we imagine for a second that instead of doing all of this on a single thread, we do each of the additions on its own separate thread, then we can actually rewrite this code to kind of simulate this situation. So instead of having the overall count, we would have just the ID of the thread that we're doing this in. So we'll have a value I, which corresponds to one of the threads of execution that's actually doing the addition for a particular pair of elements. And then, of course, what would happen is this for loop has to be done here, like so. So we would go from 0 to count, and instead of specifying the overall count, we're saying that only take the pair of values at the index I, so at the thread I, and add them up and put them in C. And we're not spawning any threads here, we're just simulating the operation. Let's run this. Okay, so we have exactly the same result. Shouldn't be that surprising. And now we can make this conceptual jump from a CPU code to GPU code. And we need to do it in stages because it's actually not as simple as one would imagine. So the first thing we'll do is we're going to alter the add arrays function. And the way we're going to alter it is essentially by getting rid of the thread index, because the index of the thread that we're running on is actually an implicit variable. You don't need it as a parameter because it's already included inside the kernel execution. And to turn this function into a kernel, so into something that's actually running on the GPU, we need to add the keyword global, like so. You'll see it's highlighted in blue. So we're almost good to go here. The only change we have to make is we need to define this value of I, which in our case is the one of the components of a thread index, thread index.x. So essentially, thread index is a variable that contains the position of this kernel as it's executing in a thread block. So if we have a block of, let's say, 5 threads, then thread index.x, and it's a three-dimensional parameter, thread index.x would actually have values 0, 1, 2, 3, and 4 for each of these. And then we have a range of values from 0 to 4 inclusive, and we can perform the assignment. Notice that the rest of the code is pretty much the same, although we could add some const specifiers for A and B just to speed up the performance. But unfortunately, this isn't all that we need to do, because operations on memory inside the GPU have to it has to operate, CUDA has to operate on device memory, cannot operate on memory of the host machine. So essentially what we need to do after we have defined the arrays of data is we need to somehow get this data from the CPU to the GPU. And herein lies the problem. So what we're going to do, I'm going to get rid of this step for now. So what we're going to do is we're going to change the names of these variables. We're going to put an H in front of these, and H stands for host, so something that runs on the CPU, so the memory that's actually on your motherboard as opposed to your graphics card. And then we need to allocate some memory for this data to be copied from the host to the device. So we're going to have 3 pointers, DA, DB, and DC. And this is memory that's going to sit on the device. And in this case, we're going to use device memory, which is allocated using CUDA malloc. So it's a special CUDA function, CUDA malloc, which allocates memory on the GPU. So we provide a pointer to DA, and then we need to specify its size. And the size is not just the count of the elements. The size is the count of the elements. So constant size is the number of elements times their size, in which case, because we have ints, it's size of int. So we could malloc DA with the size that we've just defined, and then we do the same for DB and DC. Okay, so we've allocated some memory. Now what we want to do is we want to copy the arrays HA and HB into DA and DB respectively. And for that we need another CUDA function, which is CUDA memcpy. So CUDA memcpy, and then you have to specify the destination, so the target that you're copying to, the source you're copying from, the count, so the number of bytes that you're copying, and the kind of copying that you're doing. So we're copying to DA from HA. The size we've already defined, its size, and CUDA memcpy kind. Well, let me expand it. CUDA memcpy kind, colon. These are some of the values that you can use. So you can copy from device to device, device to host, host to device, and host to host. In this case, we're copying from host to device. So we choose CUDA memcpy host to device. And strictly speaking, you don't need that. You don't need this prefix here, so you can just get rid of it. Right, so we've done this for DA and HA. Let me copy that, and we will do it for DB and HB. So we have copied the DA and we have specified the DA and DB values. And what we can do now is we can call this function, or rather kernel. So essentially we have a kernel with the global definition as something that can be executed on the GPU but invoked from the CPU. And when invoking the kernel, the notation, it might be a bit surprising for you. So what we're doing is we're saying add arrays. And here we're specifying two values, which I'm going to explain in the subsequent parts of the module. For now, I'm going to just say that I'm going to make one block with count threads in it. So we're going to do each of the additions on a separate thread. And there's going to be just one block of these threads. So this funny notation with the triple angle brackets, you'll notice, by the way, that Visual Studio is complaining about it. It cannot actually parse this correctly, but that's not a problem. This here isn't really an error. So we're calling this method, function rather, and we're calling it with obviously the device pointer. So DA, DB, and DC, like so. Okay, so we invoke this this kernel, and the result gets placed into DC. And what we need to do is we need to copy the values from DC back to HC, so back to the host values. And for that, once again, we do CUDA memcpy. We copy to HC from DC. The size is the same, and then here we do CUDA memcpy device to host. Like so. Okay, so now that the values are back in memory accessible from the CPU, we can actually print them out as usual. So let's try running this. As you can see, we also have the correct values here, but how do you know it was really executed on the GPU? Well, one of the ways to check is to simply put a breakpoint here somewhere. So I'm going to put a breakpoint, and remember that you cannot use this kind of debugging. You have to start the end-site debugging. So that's what we're going to do. So start CUDA debugging. All right, so we're now sitting inside the kernel as a breakpoint on the GPU. Let me drag in the CUDA warp watch here, and we can actually look at some of the values. If you type in C and I, for example, you would not be able to resolve the values. And this is probably because by the time we get to this location, the value of I may not exist already. It might have been removed, but there is always threadindex.x, which is kind of, let's say it's more persistent. So we can say C at threadidx.x. There we go. And we can see that the C array actually has the right values, and we can obviously do the same for A and B. So now we have some concrete proof that this has actually been done on the GPU.